Thank you everyone for coming, and thanks to Juan for the invitation. As he just said, I'm going to be talking today about general F-theory models that have a tuned SU3 times SU2 times U1 mod Z6 symmetry and the associated generic matter with those models. So I'm going to start off with an overview of everything we need to know about F-theory to go through this talk. And then I'm going to introduce the concept of generic matter, first in 6D and then in 4D via F-theory. And then using that classification of generic matter, I'm going to talk about F-theory tunings of this gauge group with generic matter. And then finally identify a Weierstrass model that captures all of these tunings. OK, so let's start with the overview. So what is F-theory? There's several ways to define it, but perhaps the most direct is to say that it's a non-perturbative formulation of type 2b compactifications that allows for general PQ7 branes. And an important thing to note is that this opens us up to a larger class of compactifications because the compactification space is not required to be Calabi-Yau in order to preserve some supersymmetry. So the issue that leads us to using F-theory is that in type 2b, there's an axiodilaton field, a complex combination of the axion and the dilaton, and it is magnetically sourced by 7 branes, which means that in a general 7-brane configuration, you'll have a non-trivial background, and the back reaction of these 7 branes means that you can't have vanishing Ricci curvature, so the usual Calabi-Yau compactification won't work here. The insight is that the axiodilaton transforms under SL2Z in the same way as the complex structure of a torus under modular transformations. And so we can just keep track of tau by putting an elliptic curve, a torus with a marked point, over every point in the compactification space and use that elliptic curve to keep track of the variation of tau. And this leads to what's called an elliptic fibration over the compactification space B. So what does this look like? Here's a little picture of this elliptic fibration. So we have an elliptically fibered Calabi-Yau n-fold X, which means that over every point in the compact base B, there is a torus, which is the elliptic fiber shown here. And each of these tori has a marked point, which is what makes it an elliptic curve. And these all together form a section, which is just an image of the compact base in the total space X, which includes the compact base and all of these elliptic fibers. This is mathematically described by a Weierstrass model. So we have our elliptic curve as the solution to this equation with X, Y, and Z coordinates in an ambient projective space. And here F and G can be thought of locally as functions on the base. They're actually sections of line bundles on the base. So this allows us to have an elliptic fiber that is fibered over every point in the base. And what we're interested in is where the fiber of this elliptic fibration becomes singular. So at codimension 1, for example, along this red curve shown here, when the fiber becomes singular, that means that there are 7 branes wrapping this codimension 1 divisor. And this gives rise to a gauge group. So here are your singular fibers over this codimension 1 locus. At codimension 2, if we have enhancement of singularities, then this gives rise to massless matter. And you can talk about what happens at higher codimension, but this is what we're going to focus on for this talk. OK, so why is F-theory a useful tool to us? I already said that it opens us up to a larger class of compactifications. But it also allows us to make global statements about the moduli space of 6D and 4D theories. So in 6D, we have a connected moduli space. And F-theory allows us to make statements like the fact that in large branches of the moduli space, there are generically gauge groups that cannot be Higgsed. So from the field theory point of view, these are gauge groups with matter content that can't satisfy the D-term constraints. So you cannot Higgs these gauge groups while preserving supersymmetry. In the geometric picture, it just means that at a generic point in the moduli space, these gauge groups will be present. And there are typical factors that show up in these non-Higgsable forms. There are also other gauge groups, such as SU5, that always require tuning. They don't show up as non-Higgsable gauge groups. And then further, there are gauge groups like SU500 that you can't tune at all. Most branches of the moduli space have large non-Higgsable groups with many factors of these various simple groups. And these are candidates for hidden sector dark matter in a model building context. So at the geometric level, we can say similar things about 4D, but it's a bit more complicated there because the moduli in general are lifted by a superpotential, so we no longer have this one connected moduli space picture that was so nice in 6D. And then in addition to the geometric data, you have to include fluxes, and the fluxes in the superpotential can affect these non-Higgsable clusters. Okay, so the last thing I want to touch on in the overview is different approaches to trying to find the standard model in the F-theory story. So basically, there are two binary choices you can make. Do you want to do something non-Higgsable or tuned? And do you want to do a gut? Or do you want to directly get the standard model? So for example, you could try to use a non-Higgsable E8 factor and then break it with fluxes to try to find the standard model. You could instead try to directly find...
Non-Higgsable, how do you break it? You mean non-Higgsable in 6 dimensions?
Yes, in 6 dimensions. Oh, well, in 4 dimensions, you break it with fluxes. But yeah, the story is a little more complicated there. But yeah, non-Higgsable 6D gauge group, yeah. You could instead try to directly find SU3 times SU2 as a non-Higgsable gauge group and then see what you get from that. Or you could go the tuned route and, for example, try to tune an SU5 and then break that down to the standard model. Or you could directly tune SU3 times SU2 times U1. And this is what we're going to be talking about today, is a directly tuned standard model gauge group. OK. So the next thing I want to talk about is this generic matter classification, which is going to be a useful organizational tool for us going forward. So let's start in 6D supergravity, where we can get a really concrete handle on what generic matter should be. So here, I'm going to fix a gauge group and fix some anomaly coefficients that go into the anomaly cancellation conditions. And then given those choices, I'm defining generic matter as matter that exists in the highest dimensional branch of this connected moduli space that we see in 6D. In the field theory language, this is the space of uncharged massless scalars. So I'm fixing a gauge group because, as I said before, there are these generic non-Higgsable gauge groups. And so we want to choose a gauge group ahead of time, so we're separately answering the question of what matter is generic, given a choice of gauge group, distinct from the question of what gauge groups are generic. OK, so as a few examples, if we just have a single SUN factor, the matter representations that turn out to be generic are the fundamental, the adjoint, and the 2-index antisymmetric. For a U1 gauge factor, the generic charges are charge 1 and charge 2. So these are sort of the simplest representations we expect to see, and they do turn out to exist in this highest dimensional branch of the moduli space. In 6D, we can say more about these.
What limits the charges of the U1s?
Say again?
What limits the charges of the U1s?
So these are just limited to these generic matter representations. You can get charge 3 and charge 4 and so on, but they're not generic in a sense that I'll see very concretely on the next slide. Yeah. So for large classes of gauge groups, the number of generic matter representations matches exactly with the number of non-trivial anomaly cancellation conditions. So here, for example, are the 2 non-trivial anomaly cancellation conditions for a single U1 factor. And as we saw, there were 2 generic matter representations. And what this means is that in general, we can solve the anomaly cancellation conditions exactly for the multiplicities of hypermultiplets charged under the generic matter representations. And this leads to anomaly equivalences. So if you just look at these 2 equations, you'll see that the anomaly contribution from 6 hypermultiplets of charge 2 and 10 of charge 0. This comes from an additional gravitational constraint on the total number of hypermultiplets. Gives the exact same anomaly contribution as a single charge 3 multiplet and 15 charge 1 multiplets. And so here directly we can see why charge 3 is not generic, because in order to move in moduli space to increase the number of charge 3 multiplets by 1, I had to consume 10 chargeless scalar fields, which are our moduli. So we lose 10 moduli to move to a branch that has an additional charge 3. So that's what I mean when I say that charge 1 and charge 2 are generic, and no other representations. OK, so now I want to connect this to F-theory. It turns out that this generic matter classification matches exactly what we expect to come from the simplest F-theory constructions, those that have the simplest singularity structure. So for example, the generic SUN tuning is done via a Tate model, where you have this equation, which can be turned into Weierstrass form if you just complete the square on the left and complete the cube on the right. For a given choice of capital N, there's a prescribed set of little ni, such that if I tune the A1, 2, 3, 4, and 6 to vanish to appropriate degrees, then I will get an SUN model with exactly the generic matter. There is one recently discovered exception, although if you actually do a careful counting of the number of degrees of freedom, in that case, you can see that it is tuned to give you the exceptional matter, the exotic matter. For U1, there's what's known as the Morrison-Park model. So this is given in Weierstrass form here. This is the f and the g, these local functions on the base. And these give U1 models with charge 1 and 2, which exactly match our 60 supergravity definition of generic matter. OK, so now we want to generalize this concept to 4 dimensions. But unfortunately, we can't just use the same definition we did in 60, because, as I said, the moduli space is lifted by the superpotential. And we also can't use a counting of the anomaly cancellation conditions to try to find the cardinality of the appropriate set of generic matter, because anomaly cancellation is weaker in 4D. But all of the arguments we made about F-theory still hold here. So arguments about the moduli space dimension for the underlying Calabi-Yau and the complexity of the constructions, which suggests that the generic matter for a 4D F-theory model should be exactly what we see in 6 dimensions from supergravity or from F-theory. And so this is going to be our working definition of 4D generic matter. It's going to be generic F-theory matter in this sense. So basically, this is just saying that we have the same representations we saw in the generic matter classification in 6 dimensions. Again, for a fixed gauge group, which in our case will generally be tuned. OK, so as you saw in the title of the talk, I'm going to be tuning SU3 times SU2 times U1 with a Z6 quotient. So I'm going to be interested in what happens to this generic matter story in the presence of these discrete quotients. And we find that in general, the global structure of the gauge group does affect what matter representations turn out to be generic. So here's a table of the generic matter representations for just SU3 times SU2 times U1 in the left column, and in the right column with the Z6 quotient. And if you look at this, you'll see that the standard model matter that we observe is not in the left column, but it is in the right column. So here you have your left-handed quark doublet. Here we have right-handed quarks. But if you look at the corresponding representations on the left side, the hypercharges are incorrect. So this is the reason that I'm going to be focusing on this global structure for the gauge group. This gives an argument that this is the more natural construction, because at least in F-theory, if you wanted to try to tune an SU3 times SU2 times U1 with no Z6, and you wanted to get the standard model matter, you'd have to do a more exotic tuning in order to achieve that matter, because you'd be leaving the realm of generic matter here. OK, so that leads me into considering F-theory tunings of this gauge group that have generic matter. Yes?
Just to orient us, in the supersymmetric standard model, from a low energy point of view, would you say that the model is tuned or not?
I
tuned model, unless you're going to say that it can have a superpotential that kills all those predictions.
Yeah, so I would say that it is more tuned if this is the global structure of the gauge group than if this is. There's additional questions like what you're talking about to say whether or not it is tuned. But by this definition of generic matter, trying to determine whether we're on the highest dimensional branch containing these matter representations, I would say that this model or models with this gauge group and this matter content are more generic, less tuned than models with this gauge group, but having this matter content.
So the idea between tuned and generic matter is that if you have tuned matter, you can give a vev to something and realize the generic.
Yeah, so you can well, it's most clear in 60, but yeah, you can move in moduli space to increase your to get rid of these more exotic representations and gain moduli. You can move to a higher dimensional branch of the moduli space. So you might picture it something like this. Your moduli space might have a large branch of higher dimension that contains, what did I say the multiplicities were here? 6 charge 2 and 10 charge 0. And then you can move to a point or to a smaller dimensional branch on which you will have a charge 3 and 15 charge 1s. So this is distinct from the picture for generic gauge groups where tuned gauge groups live on a subspace of the space that contains the generic gauge group. Here, these live on different branches.
Right, so if you give it to generic matter, then you'll actually break the gauge group to something smaller.
Yes, that's just determined by the charge of what you give a vev to in the usual way. So whether it's exotic or generic, you just look at the charges, and whatever leaves that invariant is the remaining gauge group after giving a vev. So that's the same story, generic or exotic. OK, so now let's consider these generic F-theory tunings of this gauge group. So again, I'm going to start in 6D where I can get the most intuition. And I'm going to start out just by solving the anomaly equations. So I'm going to fix anomaly coefficients. This is a coefficient associated with the gravitational coupling, and then we have couplings associated to each of the SU3, SU2, and U1 factors. And then for convenience, I'm going to define some new variables in terms of these. You could just as well keep working with these variables, but your expressions would look worse, and they wouldn't fit horizontally on the slide. Yeah.
Where does this A, B,
Yeah. So if we look at these are what appear in the left-hand side of these coefficients. And so the A gives you, so in 60, you have these anti-symmetric B fields, which live in the tensor multiplets. And these are anti-symmetric 2 forms. And A gives the couplings for the B wedge R terms. So that's the coupling in front of those. And then B is in front of B wedge F. So in the general case with multiple gauge factors, I'd have a B sub I. So I have a B sub 3, a B sub 2. And then just by convention, we name the would-be B sub 1 B twiddle. So here's a gauge condition and then a gauge gravitational condition.
These models have no tensor.
So right now, I'm leaving that general, although I'm about to specialize to the case with no tensor multiplets. Yeah. In the next bullet, actually. So before that specialization, though, we can just solve the 60 anomaly cancellation equations. There are 10 non-trivial conditions, and there are 10 charged generic matter representations. And we find these multiplicities for these various matter representations. This is the number of hypermultiplets charged under this representation. OK, so now I'm going to specialize to know tensor multiplets, so t equals 0. Because this case is even simpler, so now these A, B3, B2, and B twiddle are just numbers. A in particular is -3. The choice of B the various b is what gives me different possible solutions to the anomaly cancellation conditions.
Where are they before they were numbers? Before they were numbers?
No, so they actually live in an SO1 comma t space, where t is the number of tensor multiplets. So they're numbers when t is 0. Yeah. You can think of them as the BPS charges in the string lattice of the gauge and gravitational instantons. Yeah. So setting t equals to 0 actually makes these numbers rather than SO1t vectors. And now I can get some intuition by looking at these multiplicities. So I know that each of these multiplicities needs to be non-negative. I don't want a negative number of hypermultiplets charged under any given representation. And if I want my gauge kinetic terms to be of the appropriate sign in the Lagrangian, then it turns out that I need B3 and B2 both to be non-negative. So then I can look at these multiplicities and say, OK, I want this multiplicity to be non-negative. B3 has to be non-negative to have the appropriately signed gauge kinetic term. So x must be non-negative. Similarly, this line tells me that y must be non-negative. And then, using those facts, I want to look down at this line. There are two possibilities for this multiplicity to be non-negative. Either beta is greater than or equal to 0, or y is 0. Or both. These are not mutually exclusive classes, but it turns out that they will be useful. This is a useful split of the solutions into two classes, and some solutions will lie in both classes. OK, so this is intuition that I gained from t equals 0, but I'm going to end up using these classes in the more general case in 6D and in 4D. So first, let's look at these two classes of models in 6D, specifically with 0 tensor multiplets. So with t equals 0, there are 98 solutions to the anomaly cancellation conditions. And they all fall into one or both of these classes. And it turns out that we can construct them all in F-theory. So there's no swampland. So class A was this beta greater than or equal to 0 class. And I'm going to call these SU4 times SU3 times SU2 type, because it turns out that all of the models in this class are unhiggsable to SU4 times SU3 times SU2 models. There are 71 t equals 0 models in this class. And it is a 3-parameter family of solutions, which are B3, B2, and then beta, which was defined in terms of the B's and the A. And these B4, B3, and B2 capital are exactly the anomaly coefficients of the 4, 3, and 2 factors in the unhiggsed model. And so now we can tune these directly in F-theory because we know how to tune products of SUN factors with generic matter. So we just do a Tate tuning of SU4 times SU3 times SU2. And then we can Higgs that on 2 pairs of bifundamental matter to break down to the SU3, SU2, U1 mod Z6. And it'll give us exactly all of the models in this class. OK, so the second class of models is y equals 0. I'm calling these F11 type for a reason that will become clear shortly. There are 30 t equals 0 models in this class. So if you look at this and this and this, you see that there are 3 that are in both classes. This is a 2-parameter family, so it's the smaller of the 2 families. To match up with the literature on the F11 type constructions, we can call these S9 and S7. But they're just in terms of the anomaly coefficients we defined on the last slide.
These parameters are discrete parameters, right?
Yes. Yeah. So they lie in the string charge lattice. All models in this class are realized using what's called the F11 toric fiber, which is why I'm calling these F11 type models. So there's a thing called Bodyrev's construction where you can construct an elliptic curve as a hypersurface in a 2D toric variety. And there are 16 ways to do that. The 11th one, named F11, gives you exactly these type of models. So if you take the elliptic curve defined in that way and then fiber it over your base, then you'll get exactly this class of models. All but 3 of the models in this class, unfortunately not the same 3 that are also in class A, are also realized as petit Salam models. So you can un-Higgs them with these B4, B2, and B2 prime anomaly coefficients to an SU4 times SU2 times SU2 mod Z2 model. And then that'll Higgs down to exactly this class of 3, 2, 1 mod Z6, save for these 3 models that don't fit into this classification. And then particularly interesting is a particular model that's been discussed recently by Miriam Kvetich et al. When you take B3 and B2 both to be equal to 3, this is in the t equals 0 case, then the model is of F11 type, as are all the models in this class. It's also of petit Salam type, and it can be un-Higgs to an SU5. Which means that, at least from the field theoretic point of view, and we expect at this point in the F-theory point of view, this exhibits the possibility of gauge unification. OK, so now I want to talk about 4D F-theory models with this gauge group. And I'm going to use those same 2 classes as sort of my guiding light here. So generalizing these classes to 4D, I'm just going to use the same constructions that I use to achieve all t equals 0 models in 6D. So I'm going to construct class A as deformed SU4 times SU3 times SU2 models. And we find bounds coming from F-theory called the Tate and Kodaira bounds on how much these BI can vary. So we can just enumerate all of the models over a particular base by just running over the full allowed range of BI. And in this case, the matter curves are the multiplicities are generalized to matter curves. So we saw on a few slides ago that the multiplicity of the left-handed quark doublet representation was B3 times B2. In 4D, this is no longer supported just at a point in the base. It's supported along a curve. So this is promoted to an intersection of surfaces B3 and B2. But otherwise, we can just read off these matter curves from the table we saw before of multiplicities in 6 dimensions, with some nuance with regard to the adjoint multiplets.
That
Yeah.
gives you the matter curve, but not the multiplicity of.
Right, the multiplicity comes from sheaf cohomology arguments, so that's a lot more detailed than I was going to get into here. But just to say that you can extract this information in sort of a direct way for free in 4D from the representations in 6D. But yes, this doesn't give you the multiplicities.
Okay, so sorry, what's the geometric meaning in 4D of B3 dot B2?
Yeah, so it's promoted to an actual intersection. So remember I said codimension 1 is where we give rise to gauge groups. So if our base is 2 complex dimensional, which is the case when I want to have a 6D spacetime, then codimension 1 is just a curve. And then codimension 2 is just a point. And so at the point, I can actually give you exactly the multiplicity just from this intersection number. But if I want a 4D spacetime, now codimension 2 is actually a curve. So B3 and B2 are actually surfaces here. Yeah. OK, and just an important note, because the chiral matter is determined by fluxes that are added in addition to this geometric data, even though there are non-MSSM representations that are present in this generic matter story, they are not necessarily chiral at this point. That is determined when we add fluxes in on top of this story. OK, for class B, I'm going to either construct them from the F11 fiber, which has been discussed a lot before, or in most cases, I can tune a petit Salam via Tate tuning and then deform that. So this F11 construction has been talked a lot about before to construct 3 generation models in F-theory. And in particular, this special SU5 case I talked about, the generalization of B3 equals B2 equals 3 that we saw in 6dt equals 0 is to set both of these to minus k, which is the anti-canonical divisor class. And this was recently talked about in great detail in this paper, Quadrillion Standard Models in F-theory, which Miriam and Jim and all wrote. It's a very nice paper. And they get a lot of distinct standard models just because this model works over all weak Fano bases. So the Weierstrass model they write down can be put on a large choice of bases, and it'll work just fine. OK, so this is a special case of our class B constructions. Okay, so what have we done? Now we have broadly talked about generic F-theory tunings that we expect sort of from anomaly cancellation and the fact that we know how to tune products of SUNs and we know how to do this F11 toric fiber construction. But it'd be really nice to have an explicit Weierstrass model that describes all of these different models. As I said on the first or second slide, that is our mathematical description of this. So we want to be very explicit and find a Weierstrass model. Okay, so the question is, can we identify a Weierstrass model that has this gauge group and is generic in the sense that it gives us generic matter representations? And we also want it to be the most general possible such Weierstrass model. This would be analogous to the Tate models for SUN and the Morrison-Park model for U1. So what do we want from this? It should give us generic matter and have this gauge group, as we said. And this is the sense in which we want it to be most general. It should capture all of the moduli. So this is easily checked in 60, where anomalies give us a counting of the number of uncharged massless scalars we expect. So all we have to do here is count the number of moduli in the Weierstrass model and then match them with what we expect from 60 anomaly cancellation. This can be done pretty directly for Tate form for SUN, so SUN factors are not too bad. But U1 factors are a little bit more complicated because, for example, Morrison-Park is a redundant parameterization. So a naive counting of the degrees of freedom will overcount the moduli that are present. But you can do it using a Jacobian argument that I'm going to come back to when we talk about our Weierstrass model. OK, so how are we going to try to find this Weierstrass model? So the naive approach, the brute force approach, is to just try doing a Tate tuning of SU3 times SU2 and simultaneously doing a Morrison-Park tuning of the U1 factor and then trying to combine these in such a way that you enforce the quotient structure to be present. This is pretty hard. We tried to do this for a while, trying to make sure that the Mordell-Weil group of rational sections had Z6 torsion, which would give us this quotient structure. But we didn't make a lot of headway doing that. But a lucky miracle happened, and we noticed that an already written down Weierstrass model, Nikhil Raghuram's charge 4 U1 model that has charges up to 4, unhiggses directly to SU3 times SU2 times U1 mod Z6. So his charge 4 model has some very, very large F and G functions, which are too large for me to put on the slide. But if I take 2 of the parameters in his F and G and tune them to be identically 0, then I find this F and G, which define a Weierstrass model for me. And this has various parameters BI, DI, and SI.
The things you had to tune, were they feeds in the standard model? Or
Yeah, so
standard model representation,
yeah, so this tuning does an unhiggsing. The corresponding higgsing is to take.
No, I meant this
sorry.
one, the unhiggsing.
Mm-hmm.
So are you setting to 0 verbs of things that you already said?
Yes, so this corresponds to, so these are vevs of, it's matter that is charged under the fundamental of SU3 and has hypercharge, and matter that is charged under the fundamental of SU2 and has hypercharge. Those are the vevs that we are setting to 0. Pairs of each of them. Yeah. To do the higgsing, you have to give them non-zero vevs. And that leads us to this Weierstrass model. So now we want to ask about the features of this Weierstrass model and see if it's the Weierstrass model that we want. So first, we can confirm that it does have the proper gauge group. So you can find the loci where your fiber becomes singular by looking at what is called the discriminant. So it's this combination of F and G. And wherever this vanishes, you have singular fiber. And we find that for this Weierstrass model, this is proportional to B1 cubed times D0 squared, which after a checking of a monodromy condition tells you that this does have an SU3 factor and an SU2 factor tuned respectively on the locus B1 equals 0 and D0 equals 0. And you can identify that there is an additional section beyond the 0 section that's required for this to be an elliptic fibration, and that section is non-torsional, which gives us the U1. The quotient is subtle. It seems that there actually might be two different ways to get this quotient, either by having Mordell-Weil torsion or due to a fractional part of what's called the Scioto map. We're still nailing down this part of the story, but the fact that we have the matter representations that we do see with this model indicates to us that the quotient should be present. OK, the next thing we want to do is count the moduli. So as I said, this is kind of difficult if you just count naively because you have an overparametrization. But what we can do to try to count the moduli here is to fix a particular instance of this model by choosing a base and then randomly choosing divisor classes for all of the parameters in this Weierstrass model. Then we parameterize the variables in f and g as some w sub j, and parameterize all of the degrees of freedom in the b, d, and s variables in terms of some nu sub k. And then the dimension of the image of this j, the rank of the Jacobian j, gives the dimension of the moduli space around that fixed model. So essentially, we're going to a random point in moduli space and then looking at its tangent space and seeing what the dimensionality is. And assuming we didn't get really unlucky with our random choice of these parameters, then this should count the moduli properly. And so we've done this over many different bases with thousands of different choices of random models, and we always get the exact same answer, that this does actually capture all of the moduli. So we believe that this is actually the most general Weierstrass model that has these properties. We see that it does include both of the classes of models that we identified in the last section. So you can identify the parameters of the Weierstrass model, B1, D0, and S1, with the anomaly coefficients, B3, B2, and beta that we talked about in the last section. And you get exactly those classes of models. And particularly exciting, we see explicitly in the Weierstrass model that the special SU5 case that we identified before does exhibit an explicit SU5 unhiggsing. And it's not what you would naively expect. It turns out to be pretty subtle. The naive expectation would be that you just want to tune these SU2 and SU3 to correspond with one another. So you would just set D0 equal to B1. But if you just try to do that, it turns out you unhiggs to SU5 times U1. So what you actually have to do is do a shifted version of that. You set D0 equals to B1, shifted by some other epsilon times B2 twiddle, with epsilon having trivial homology class. And you do similar redefinitions for all of the other parameters in the Weierstrass model. But because epsilon is trivial, you can put it in inverse powers in these redefinitions. And then naively, you wouldn't be able to set epsilon to 0, but it so happens that with the appropriate redefinitions, all of the inverse powers of epsilon cancel in f and g. And so you can safely take epsilon to 0, and it is in that limit that you get an SU5 enhancement without the additional U1 factor. So this is exciting because we can explicitly see in our model that the SU5 unhiggsing does exist. OK, so this Weierstrass model we now believe gives a general construction, possibly the most general construction, of tuned SU3 times SU2 times U1 mod Z6 4D F-theory models over any given base B3. As an example, you could take the simplest case, just choose B3 to be complex three-dimensional projective space. And then by running over that range of BI that I mentioned that's bounded by the Tate bound, you find there are 181 class A models, 54 class B models, and 6 in the overlap. So we can just find all of these explicitly. This generalizes the base-independent toric construction of the standard model coming from that quadrillion standard models from F-theory story, where they were discussing only the SU5 special case. And as they saw in their paper, this construction works over all weak Fano bases. But additionally, for the class A models, it works over many bases that have non-Higgsable gauge groups as well, which would be hidden sector dark matter. And there are many, many such bases. this has been discussed in various approaches in previous papers. So this opens us up to a very, very large class of standard models in F-theory. OK, so in this talk, what I have done is first started by defining generic matter rigorously in 6 dimensions and then generalizing it to 4 dimensions via F-theory. And then using this as an organizational principle to identify classes of general supergravity and F-theory models in 6 and 4 dimensions with this particular gauge group in generic matter. And again, we chose this gauge group because the generic matter includes the representations of the standard model. I found 2 classes of such models. The larger class was this 3-parameter set, which unhiggses to SU4 times SU3 times SU2. And this is compatible with non-Higgsable gauge group dark matter, as I said on the last slide. The second class, which was the smaller class, can all be constructed using the F11 toric fiber or mostly via deformed petit salam. This gives you access to this more explicit toric construction, which gives you a lot of nice combinatorial tools for investigating properties of these models. And it has fewer non-standard model matter representations, because this corresponded to setting y equals to 0, which turned off several of the multiplicities for these non-MSSM representations. We then found a single Weierstrass model that unifies both classes. And we therefore expect that if the standard model is tuned, as opposed to being non-Higgsable and not from some flux breaking of a tuned or non-Higgsable gut, then this is the form that it should take in F-theory. So thank you for your time.